We present a novel post-processing approach for radiometric self-calibration of video. Given a video without prior knowledge about the camera nor its settings, our algorithm radiometrically calibrates the input, undoing the effects of nonlinear, time-varying changes in intensity and white balance. Another motivating result for a video recorded with a mobile phone. Radiometric self-calibration aims to recover the camera mapping of incoming irradiance of scene points to intensity values that constitute the final image. This mapping, known as the camera response function, is highly nonlinear, mainly due to the in-camera post-processing including tone conversion, white balancing, and gain adjustments. Radiometric calibration consists of the following main steps. First, Lambertian scene points are tracked through the video to obtain intensity matches. The intensity matches are then used to fit the response function, here modeled as linear combination of basis functions. Finally, using the recovered response function, the video can be mapped to radians and optionally tone mapped. Previous work assumed the response to remain constant throughout the video. To test this hypothesis, we recovered the response within a sliding window of 30 frames for a static sequence, ruling out tracking and vignetting errors. Notice how we achieve consistent exposure across windows by using a common origin to remove the exponential ambiguity. In contrast to previous approaches, we observed that the estimated response is not constant but exhibits time-varying behavior, regardless of the window size. Here, a larger window of 40 frames and a smaller one of 20. Motivated by this empirical observation, we propose a mixture model of time-varying responses placed at keyframes. Our mixture model consistently outperforms a single model as used by Kim and Polyphys. As evaluation, we measure the constancy of the recovered irradiance over time. For this, we deliberately place a color checker in the sequence, tracking it throughout original and calibrated results to measure the variance within each of the 6 top achromatic checkers. Original video at the top and our calibrated result at the bottom. The irradiance of the top 6 checkers after calibration is constant, as verified by the error plot on the right. Another sequence recorded by the same camera, exhibiting a similar evolution of exposure. Our calibrated result with error plot. We now show how video analysis that relies on consistent appearance over time benefits from our calibration, here for video segmentation. Original on top and our calibrated result at the bottom. In this static example, prior calibration increases the number of stable regions significantly. A dynamic scene recorded with an Android smartphone. Video segmentation results for original and the calibrated video. Notice a dramatic change in region stability. Another example of a dynamic scene recorded with the same smartphone. Segmentation results prior and after self-calibration. A final example. Our technique shows applicability even in presence of specular reflections. The segmented results. We qualitatively compare our results to Farbman and Leshinsky. Original on the left, Farbman and Leshinsky results in the middle, our result on the right. Our algorithm fails in case few Lambertian scene points of constant irradiance are present, for example in night shots with varying illumination. We demonstrate generality of our approach by self-calibrating several videos we obtained from YouTube. Note that texture transfer to static under or overexposed areas is outside the scope of our work. A static example recorded with a cell phone camera. An example with dominant foreground motion. The same sequence repeated. A final example.